Okay, let's get started. Good afternoon, everyone. It's my great pleasure to introduce today's speaker, Professor Monika Aidelsburger. Monika is an experimental physicist working at the forefront of quantum simulation with ultra-cold atoms. She's a professor at Ludwig Maximilian University in Munich and also leads a research group at the Max Planck Institute for Quantum Optics. A hallmark of her work is turning neutral atoms into designer quantum matter using a rich toolkit, and then using these platforms to explore many-body phenomena that would be otherwise hard to study either analytically or numerically. These range from explorations of topological physics to non-equilibrium quantum dynamics to lattice gauge theories. Especially notable are her early path-breaking experiments for the realization of synthetic gauge fields in optical lattices for simulating topological phases of matter. Her work has been recognized with multiple honors, including an ERC starting grant, the Alfred Krupp Prize, and the Wilhelmine Science Award. Sorry for butchering the name. Okay. So today she'll describe some exciting frontiers in quantum simulation with these platforms and the new physics that's opened up when topology, interactions, and dynamics can all be controlled atom by atom. So please join me in extending a very warm welcome to her.
Thank you very much for these kind words and for this invitation. I'm very happy to be here and be able to present some of our work. In particular, I'm also happy to share some of the recent results. Actually, I included some pictures, which I just got this morning from my team. So yeah, please feel free to ask questions just in case something is unclear, because I haven't really talked about this very often yet. As Monika mentioned, I will be introducing our quantum simulation platform, which is based on neutral atoms and optical lattices. And then the plan is to introduce the method on how to simulate gauge fields and topological phases of matter. And then at the end, I want to talk a little bit about lattice gauge theories and dimer models. Before I start, I would like to zoom out a little bit just to put this field into context. So what we do is quantum simulation. And I'm sure you're all following also in the news, like this hype about quantum technologies or our hope in developing new applications based on quantum systems. And really the new ingredient that we want to make use of is interactions between particles. So we know already for a while how to control individual qubits, particles, photons, ions, superconducting qubits. And now really the challenge is to put systems together in the lab where we can microscopically engineer and control the interactions in a way that we have interesting quantum systems that are useful for applications. And that really includes a very broad range of applications. I just give a few examples, but it's related to material science, understanding emergent properties in material science, developing quantum computers that hold the promise for being able to more efficiently compute things that we might not be able to do classically. And there are a range of applications in sensing, communication. But as I mentioned, really what we want to make use of is large quantum many-body systems that interact and create entangled many-body states that are useful for something. But now the challenge is a little bit that in order to be able to do that, we need to understand the properties of the system. We need to, if you want to build or develop something in the lab, you need to know what you're doing. But there we already face the challenge that we cannot solve them classically. So we already have to make use of approximations somehow. If we compute how many coefficients or states there are just for 300 particles, we easily end up with crazy numbers like 10 to the 90. And obviously, we cannot just perform exact numerical simulations. We have to incorporate approximations. And since this is sort of the hope in order to develop quantum technologies, but also the challenge to begin with, and even to understand them, there's the idea that we could use quantum simulators. So why not build controlled quantum systems in the lab that can give us answers to some of these questions? And we can actually study controlled approximations, build intuition, and then develop technologies based on these platforms. And there are a variety of different pathways that you could follow in order to build these systems. So these ideas go back to Richard Feynman. And I have just selected random 4 pictures here. There are many, many groups and many, many platforms around the world that work on this topic, and they don't fit on the slide, but I already mentioned a few of them. And you actually see on that slide where I have superconducting qubits, trapped ions, atom arrays, neutral atoms, and optical lattices, that they are at the interface of what we call quantum simulation. I will say more about this later, and quantum computing. So they really, there are a lot of overlaps in techniques and methods, and usually both platforms sort of explore both of these regimes. I will be focusing on atoms and optical lattices. And the first thing I would like to do is explain the platform and also explain the pictures that you see here. So I can already tell you that what you see here is the fluorescence image of atoms trapped in a periodic array. So each one of these little dots is one cesium atom that scatters a few thousand photons. And this is the starting point for the experiments that we perform in order to study synthetic quantum matter. So we tailored or designed quantum matter in the lab. So how these systems are built is that first we cool them to very low temperatures, to few nanokelvin temperatures, and then we load them into these optical potentials. How they are formed is by interfering laser beams. So the simplest configuration is having a counterpropagating laser beam that creates a standing wave, and then the atoms see this as a potential energy landscape. And the distance between these neighboring sites is extremely short. It depends on the wavelength of light that you use to generate the interference pattern in the first place. And typically this distance is on the order of 0.5 micrometer. And while this is large compared to actual solid state or condensed matter system, where the lattice constant would be on the order of angstrom, so we actually have the opportunity to build microscope objectives and look at individual atoms, it's still very, very challenging. It's really on the edge of what you can do with optical high NA imaging systems if you think about resolving this small distance of 0.5 micrometer in the lab. The reason why the distance needs to be so short is that here we work with particles that can move between neighboring wells, as opposed to some of the other systems that you may have seen, Rydberg atom arrays, where the distances are much larger and interactions are introduced in a different way. Okay, so here we are dealing with these periodic potentials where we trap atoms. And if the temperatures are low enough and we adiabatically prepare these systems in these potentials, then the dynamics is governed by simple parameters, J, the tunnel coupling between neighboring sites, and U, the Hubbard on-site interaction energy. So you have this many-body system of atoms that can move around and interact when they meet on the same site. And in the simplest form, the natural Hamiltonian that we get when we prepare the system is a Hubbard-type Hamiltonian. And these two parameters can be controlled independently, so we can perform dynamical experiments, but we can also perform adiabatic phase preparation ramps. And so a lot of what I want to tell you about is actually how to make this Hamiltonian a bit more interesting. So because this is the one that we get more naturally, but it's topologically trivial, for instance. And I want to tell you a little bit about what we can do in order to modify the properties of these systems. This is a schematic of how such an experimental setup actually looks like. So the whole preparation part is skipped. So the laser cooling and trapping is skipped. This is the final setup. So it's the final vacuum chamber where we have ultra high vacuum conditions on the order of 10 to the minus 11 millibar. And this science chamber is fully made of glass. It has 11 side ports and 2 top and bottom windows that are very close to the atoms so that we can build high NA imaging objectives for manipulating, but also imaging the atoms. And so you see laser beams that come in from the side. They form this standing wave geometry. And then we also have laser beams that confine the atoms out of plane. So typically we work with 2-dimensional systems because they are easier to manipulate with high resolution using high NA imaging systems. Now, in order to take pictures of these atoms, what we do is we freeze the dynamics. So the way these experiments work is that we perform some quantum many-body experiment. We have a wave function that describes our atomic system. And then we freeze the dynamics. We make the lattice very, very deep so that the atoms cannot move around anymore in this potential. And then we scatter near resonant photons in order to collect images that look like this. And what happens during this imaging process is that we measure in the occupation basis. So if we describe this many-body system as a wave function that is a superposition of different occupations, then we project onto one of these configurations. And if you want to get information about the mean density on a specific site or density-density correlation functions, we essentially sample from this quantum many-body wave function. So we do a quantum simulation experiment, and then depending on what observable we want to measure, we project, we take an image, and then we repeat this process many, many times in order to extract information about the system. And I think what is special is that for us in these quantum simulation experiments, it's relatively easy to scale up the number of particles. So typically we work with about 2,000 or 3,000 atoms in that lattice in a two-dimensional geometry, and the coherence times can be really long. So if we extract the coherence time in terms of interaction times, we can reach 100 or 1,000 interaction time scales, which is large compared to what typical digital quantum computing devices can do nowadays. So there's some competition, but these devices are really very powerful when it comes to system size and coherence time. Okay, so there have been a number of different experiments and applications already for these neutral atom quantum systems. I want to talk about two of them that I already mentioned, which are very dear to my heart. One of them is topological phases of matter, which is the first one that I would like to talk about. And this is particularly interesting because there are many strongly correlated phases of matter that exhibit topological properties, which are extremely hard to describe theoretically. And often there are just trial wave functions that one can write down analytically to try and understand the properties of these phases of matter. So this is a very nice area for quantum simulation if we are able to simulate the properties of some of these phases. Another area that is very actively studied also by my group is quench dynamics or out of equilibrium dynamics. And those dynamical or experiments are extremely difficult to simulate numerically. And those are rather natural for us to do because the way that these experiments work is that we prepare a certain configuration of atoms in the lattice, and then we study time evolution. And then we can ask fundamental questions about, does the system thermalize? Does it localize? Is it non-ergodic? Can we store information in this quantum many-body system? And we can essentially just watch the properties of the system as time goes on. While numerically, this can be very challenging to simulate because there's entanglement and information spread in the system as we go to longer and longer timescales. And the last part, which is sort of the new topic that I also included for this colloquium today, is studying lattice gauge theories or local symmetries in this model in general. And I will focus on one specific application, which is quantum dimer models. Okay, just to emphasize this again, because it distinguishes quantum simulation from universal quantum computing, the way you should think about this is really that we engineer the microscopic terms. So we engineer the microscopic interactions between the particles in a Hamiltonian form. We don't apply gates or digital time evolution. So the physics that we can access is really determined by what types of Hamiltonians we can engineer. All right, so I will focus on these two topics and start with the first one. And the question is, how can we actually simulate topological phases of matter in these Hubbard models? And how should we even think about these systems? And I will start with a very, very simple example, just to have everybody on the same page, and then try to explain to you how that looks like in our atomic system. And the most well-known example for topological phases of matter is the integer quantum Hall effect. So you can think about it as Hall bar geometry that is displayed on the left, two-dimensional electron gas, where you can measure voltages, longitudinal and transverse voltages. And what you do is you send a current through the sample and there's a perpendicular magnetic field. Now you know that when we have charged particles, there's a Lorentz force, so the atoms get deflected. And in the classical regime, if we measure the Hall voltage and plot it as a function of the applied magnetic field, there's a linear dependence. And this is what you see here on this plot. If we measure the transverse resistance, there's this linear behavior with the applied magnetic field. Now, if we go to the quantum regime, something interesting happens. There are these plateaus that develop, and these plateaus are extremely robust. And this is where topological properties come in. So in a nutshell, what determines the value at the center of this plateau is the topological invariant that characterizes the band structure that is occupied by all the electrons. So there's an integer number that you can assign to each band that is occupied and fully filled with electrons, and you sum up all of these integers, and this gives you the number of the transverse Hall resistance at that point. So I also like to show these pictures typically, just to emphasize why it is actually so remarkable that we can measure these quantities with an uncertainty of less than 1 part in 10 to the 10. And if you look at this picture, this is a silicon MOSFET device. I think it's really almost crazy to expect that this is possible, because you have this two-dimensional electron gas, you have a Hall bar geometry, you send a current through, you measure voltages, you attach leads. We all know that there can be dirt and dislocations in the system, and that you can reproduce that with such precision is really remarkable. And I think this also highlights why topology is so interesting for applications. It's because of this intrinsic robustness as we also add disorder to the system. And in fact, the plateaus that you see are a result of disorder in the system. And we can discuss about how that looks like in our atomic system as well. And actually, because this is so remarkably precise, it has been used early on already in order to use it to compare resistance measurements between different labs. And more recently in 2019, now it plays an important role also the redefinition of DSI units. All of these properties of the integer quantum Hall effect can actually be understood in a single particle framework. So you don't actually need to solve any complicated equations, including interactions. We understand where these topological invariants come from, how to compute them, and we also understand how they are connected to the number of topological edge modes at the boundary of the system. However, now as we add interactions to the system, it gets even more interesting. There are now fractional plateaus in this Hall resistance. And those phases of matter that are at these plateau values really emerge due to strong interactions between the particles. And that's challenging, because that means that there's no easy perturbative way in order to understand these properties. So to include interactions perturbatively, we have to find other ways to solve them. And one way is to use trial wave functions. And these states have very interesting properties. They can exhibit topological order, exotic fractional quasi-particles, anionic statistics. So there are a lot of interesting properties that we are interested in studying in more detail, and having something like that under the microscope in a synthetic quantum system would be extremely interesting. Okay, so now the question is a little bit, okay, that's an interesting area for quantum simulation. But obviously, there's a mismatch between what I've told you in the first few slides, where we trap charge-neutral atoms into this interference pattern of light, and a two-dimensional electron gas. So if I apply a magnetic field to my system, there's no Lorentz force or anything, because the atoms are charge-neutral. So we have to find other ways in order to simulate the physics of such quantum Hall systems, or the physics of topological phases of matter in general. And I think this is a very nice example to illustrate how the process, or the idea of quantum simulation works, because now we take a step back and look at the system in a more abstract way. So what I mean by that is we can try to use the minimal ingredients, or identify the minimal ingredients that are needed in order to see these physics. So now I can think about my square lattice. I have my kinetic energy, my hopping term between neighboring sites. And I ask the question, how is this Hamiltonian different if I now think about charged particles in this square lattice in the presence of an external magnetic field? And what happens if I describe this non-interacting Hamiltonian is that the hopping matrix element between neighboring sites becomes complex. It's no longer real, but there's a phase associated with it. And the easiest way to understand this is thinking about the Aharonov-Bohm effect, where we know that if we take a charged particle and make it travel around a loop, it picks up a phase that is proportional to the magnetic flux that pierces the area of the interferometer. And similarly, if we think about this lattice, I have a discretized version of that. There's a Peierls phase that appears in the tunneling coupling matrix element. And if we go around one loop, I can compute the Aharonov-Bohm phase associated with that loop. And if it's non-zero, if it's finite and not equal to 2 pi, then I can interpret this as a magnetic flux piercing the unit cell of that lattice. And that's actually all I need to know at this point, because it means that if I can recreate that Hamiltonian in the lab by whatever technique I like, I can study quantum Hall type physics, or I should be able to see phenomena where the charge neutral particles behave as if they were charged particles in a magnetic field. And I will not go into the details on how we do this, because I also would like to present some of the newer results. But the way we imprint these phases is by periodic modulation. So we now take our Hamiltonian, we vary it periodically as a function of time to recreate a new effective Hamiltonian that exhibits the properties we want. And the way to think about this is a little bit like rotating saddle potential in classical physics. So you know that if you have a saddle potential, you cannot trap a particle. But if you start to rotate it at the correct frequency, then you can generate an effective 2D trap and trap the particle in the center of this potential. And similarly, if you start to modulate the parameters of your Hamiltonian, the time average of that can give you new properties. And this can allow you to engineer new effective band structures in your system that you can then probe with your atoms in the lattice. Okay, so this is a very, very old experiment that I still like to show, because you may wonder, okay, once you have a technique where you think you know how to imprint phases on these tunnel couplings, what's the first type of experiment that you would like to do in order to convince yourself that it's actually true? And the simplest experiment that you might think about is, well, if I have an electron in a homogeneous magnetic field, it performs cyclotron orbits. That's something that we know. Maybe we can recreate that with charge neutral atoms in an optical lattice. And indeed, that's one very old experiment that we did, where we tracked the mean atom position in the lattice after letting the atom tunnel and seeing if there's an effect of a Lorentz type force. And if there's no magnetic field, you would actually expect like a straight line. The atom would just tunnel back and forth. But what we find here is like a sort of like discretized version of a cyclotron orbit. But you see that there's a perpendicular force that acts on the atom that makes it move along a circle. Again, so this is 2011. We didn't have a microscope or any fancy techniques. By now, these orbits look a bit like this. So this has been done in 2020 by Silmana Somben in Paris using a different technique. But you really see that one can induce these cyclotron orbits. Okay, so now this is actually just showing you that indeed we can recreate such a Lorentz force. But you may wonder, well, can we actually recreate also something that looks a bit more like a transport experiment in condensed matter physics? So this is the same schematic as before. What we would do in order to measure the transverse Hall voltage is to send a current through the sample, apply a perpendicular magnetic field, and then measure the transverse Hall voltage. So how can we do that with atoms? And there's actually a very similar way to do this. And in our case, the experiment looks like this. We have a cold atomic cloud that we prepare in a non-trivial band structure that has a non-zero Chern number. And the Chern number is really what determines the plateaus in the integer quantum Hall effect. That's the topological invariant that is assigned to each energy band that is occupied with electrons. So now we fill such a non-trivial band with atoms, and we look for something similar. Now, we cannot really send currents through the sample or apply voltages, but applying a voltage in our case essentially means we tilt the lattice and apply a force. And what now happens is that if we track the in situ motion of the cloud, there's a transverse displacement, which is the equivalent of the Hall deflection in an electronic system. And we can track this equation of motion as a function of time. And it turns out that the slope of this motion is precisely given by the Chern number of the band that we have occupied with our atoms in the lattice. And this is somewhat interesting because it really illustrates what we are trying to do here. We study the properties of a model Hamiltonian that we wrote down, which we believe captures the interesting phases of matter that we would like to study, but it's very decoupled from the original system that we were interested in studying. So why do I emphasize that? Because the system that we are studying here is really very, very different from the two-dimensional electron gas or the Hall bar geometry that I started out with. Here we have charge neutral atoms, and they are even bosonic, and the band is actually filled thermally. So it's an incoherent mixture of bosons in a certain band. So it's very, very different compared to anything that you would expect from an integer quantum Hall system. Now recreated in a completely synthetic material that shows similar properties. Okay, so again, all of this actually is still non-interacting physics. And I started the discussion by saying that what would be interesting is to study fractional quantum Hall type phases. But so far, there has been none of that. And the reason why this is challenging is that the way that we imprint these phases is by periodically modulating the lattice, and that can heat up the atom. So it's very difficult to prepare these fragile quantum Hall phases in this system. And so the state of the art up to now is 2 particles. So I've put 2 examples on these slides. They have been created also in photonic systems. This one is an example from Harvard, from Markus Greiner's group, where they have realized a fractional quantum Hall type state with 2 particles. And there's another example. You can engineer similar types of physics in rotating traps, rotating gases, making use of the fact that the Coriolis force is mathematically equivalent to the Lorentz force. And also in that case, it was just 2 particles. And so the idea of these experiments really has been that we take the methods that we know that work with single particles and sort of scale them up. So we just add more and more particles. We go to 3. I know in the Harvard team, they are now, this is 2. In the Harvard team, they are now going to 3 particles, but sort of making the system slowly bigger and bigger. What we have been trying to do is take the opposite approach. We have tried to put many particles into our system and identify stable parameter regimes. And sort of the idea is that we know how the system heats up. So if you think about the strongly correlated Hubbard model, there's a large energy scale that you need to pay if you put 2 particles on one side. And you can imagine that if you periodically drive the system, if you hit one of these resonances, the system easily heats up. Like there are many scattering processes that make the system unstable. So the idea is that you stay away from these resonances and you should be able to identify a stable parameter regime. So we have tried that. And instead of like going to a large 2D system, we have started to look at a simpler version of that, which is 2 coupled chains. So that's like the simplest system that allows you to study magnetic properties or the phenomenon in the presence of an artificial magnetic field. And it turns out that these simple systems already show quite interesting physics. So let's look at the phase diagram of putting particles in such a flux ladder. In our case, again, it's bosonic particles. And so here's a 2D phase diagram. Let me briefly walk you through. So if you look at the horizontal cut, so that's the plot below, it shows the chiral current, which is a current flowing around the edges of this ladder as a function of the applied flux. So what you see is that if you increase the flux, there's the screening current around the edges of the ladder system that increases roughly linearly with the applied flux until it hits a critical point, and then it decreases. And this phase diagram is very similar to what you expect from a type 2 superconductor. So the phase where the chiral current increases linearly with the applied flux is what is known as the Meissner phase. And then as we hit a value above a critical value of the flux, these currents that previously were going around the edges and were screening the applied external field start to break up into smaller vortex structures and current profiles with increasing periodicity. Now, this is kind of surprising. You find this just by solving the phase diagram and looking at the properties of the Hamiltonian. But what you should keep in mind that there's actually no such thing as a back action onto the effective magnetic field. Like I can say the words that there's a screening current around the edges of the ladder, but it's really not that there's any field generated by the particles that have this chiral current. These particles are charge neutral, and the flux that we apply to the system is imprinted by our periodic modulation scheme. So it's somewhat surprising that we can actually resemble the properties that you would expect from a type 2 superconductor. Now, in our case, tuning the flux is very, very difficult. So instead, what we do is we tune the strength of the coupling along the leg versus the coupling along the rungs. And then you can see or probe a similar transition between the Meissner phase and a vortex phase. Now, there's another problem or like a challenge in detecting these phases. You see the way that I presented the phase diagram, that somehow the properties of these phases are really encoded in the current. or in other words, in relative phases between nearest neighbor sites. And this is something that we typically do not get from our snapshots, because the pictures that I've showed you before is really just occupations of atoms in the lattice. So you get snapshots like this, and you know that you are sampling from this occupation basis wave function. But in the Meissner phase that I've shown you, the density profile is completely homogeneous. So if you take these snapshots and average them, you basically just find a homogeneous density profile in this Meissner regime where you have the chiral currents. So in order to be able to see those currents, we actually developed a new technique in order to resolve phases between neighboring sites and not only measure occupations. And so I don't go very much into the details of how this technique works, but the basic idea is that before you take the image, you can manipulate nearest neighbor pairs in your lattice. So you can apply local operations between them, you can couple them, and that actually allows you to rotate the measurement basis. So by manipulating dimers, you can map the current observable onto occupation. So the way we tested this is by preparing chiral currents in isolated plaquette. So this is the ground state of two interacting particles on a very tiny four-side lattice. And then we tried to locally resolve these currents in our microscope experiment. And this is an actual snapshot of such an experiment. So this is an actual array of atoms that we trap in this two-dimensional lattice, where we resolve the local current distribution on individual nearest neighbor bonds. So the red arrows give you the direction of the current in the horizontal direction, and the blue ones in the vertical direction. And you get nicely the distribution in the 2D plane, where you see that indeed each one of these little plaquettes shows these chiral currents in the ground state. You also see that there are some defects if you look at the whole 2D plane, which in this case is actually purely given by shot noise. So it's if you would take more statistics and average more, all of them should give you these circulating current. So this is a very nice new tool that then allows us to study different properties of these many-body phases, and we are developing more and more of these techniques that allow us to extract more information from our many-body system. Okay, so we were then able to actually apply this to the two-dimensional system, so to study quasi-one-dimensional ladders and look at the phase diagram. And indeed, so this is what you see. So this is the experimental result that we find. It's this chiral current averaged around the bonds, and as a function of the coupling ratio K/J, where you see a transition from the vortex phase into the Meissner phase. And especially in the Meissner phase, we were able to go to relatively low temperatures because it's a gapped phase, and we can generate this by trying to avoid all the scattering resonances at rather low temperatures. And we are quite proud because this pushes us to the limit of about 24 particles, which is an order of magnitude more than what people have done so far. It's at relatively low temperatures. And we believe that this is one way now to push and actually go towards studying fractional quantum Hall systems by coupling these ladder systems together, and that we can actually really go to a many-body regime beyond two. So that would be the goal using that technique. Essentially, all of the things that I've told you so far is very much inspired by condensed matter physics and what we have already seen in solid state, essentially, because you might also say, well, we already have fractional quantum Hall states. Maybe we should just develop better probes in solid state. But the question is, maybe we can look at these systems and treat them in a more abstract way and ask if we can generate topological systems that go beyond what we already know. And sorry, there's one mistake here. And so let me briefly zoom out on how we think about these systems, or how we think about conventional quantum Hall systems. I've told you that the origin of this plateau in the transverse Hall conductance is the Chern number, or the non-trivial topology of the energy band that is occupied with electrons. And here's a very simple schematic of a two-band model where we have two bands of non-zero Chern number, and there's an edge mode that connects the two. And we know that edge modes exist at the boundary between two distinct topological phases. And there's a connection between the number of edge modes in the system and the Chern number of the bands. And so the churn number is actually given by the number of edge modes leaving the band from the top minus the number of edge modes entering from below. So what you see in the schematic is essentially one edge mode at zero energy. So 1 minus 0 from below gives you 1 for the churn number of the band in between. But now we work with periodically driven systems. So we have a quasi-energy spectrum. This band structure repeats infinitely many times, and the separation between them is given by the modulation frequency. So this is sort of a Brillouin zone in energy space. So these two dashed lines are actually equivalent. That means I can draw an edge mode that leaves the top band and enters again from below. It can wind around this Floquet-Brillouin zone, which looks like this. And now I have generated a very strange band structure where I have edge modes everywhere in this quasi-energy spectrum, but the churn number of the band, of the bulk band, is equal to 0. So if you compute the churn number, given the rule I mentioned below, it's 1 minus 1 is equal to 0. And these are very interesting phases of matter that only occur in these non-equilibrium or driven systems, which can also have very interesting properties in the presence of disorder. So it's expected that in the presence of disorder, you can have like all bulk states completely localized, but still have topological edge modes in the system. While in a conventional quantum Hall system, this is not possible. You would have directly a transition to the topologically trivial regime. So now, when we started working on this, we did Hall deflection measurements, everything that I presented before, but somehow there's like a fundamental tool missing. You really would also like to see what happens at the edge of the system. And so we developed a method that allows us to directly probe what happens at the edge by generating an artificial interface. So in order to now have a topological interface, in a real material, you would just have the interface between the material and vacuum or nothing. In our system, what we do is we project a repulsive wall into the atomic plane, such that we generate a barrier where the atoms cannot go to. And this generates an interface where you can have edge modes at this interface. Okay, so let's see how that looks like. So in this case, the dashed line basically shows the boundary, shows the interface. And we project a repulsive disk. So it's like an inverted bucket. And the dashed line gives you the outside of this inverted bucket. So this is a real space picture. And then what we do is we prepare a localized wave packet of atoms. It's a few hundred atoms in this case at the edge of this bucket, inverted bucket. And then we track the evolution as a function of time. And so what happens is that the atoms, they start to evolve as a function of time, but instead of propagating into the bulk, they wrap around the outside of this inverted bucket. And so we can track this for about 70 tunneling times. And we can also control the chirality of the modulation in this case, or the topology, like we can reverse the sign. So we can make the edge mode go the other way. And this is a difference image between the two chiralities that we apply in this case to modulate the system. I will not go much more into the details, but it has actually been quite fun to play with these edge modes because we now fully control the shape of this edge. So you can make a straight line, you can change the smoothness of this edge and see what happens to the edge mode. We also did a few fun experiments that I don't know what they're useful for, but we generated like quantum point contacts and smashed edge modes into each other and looked interference patterns between these edge modes. So there's a lot of things that you can now do because you fully control the shape of this edge mode. And we have actually also been able now to use it for something useful because if you go back to this band structure, the schematic one that I showed you before, you see that there's an edge mode at every quasi-energy. But they look different if you plot them. So they are localized at the edge or the boundary of your system, but they can have an additional phase gradient around it, in particular if they live at a finite quasi-momentum. And if you see the edge mode in the experiment, really very much depends on how well you mode match your initial wave packet to this edge mode. So you can play around with these properties and come up with a protocol that allows you to distinguish different topological phases just by using this mode matching condition. Okay, so let me give you an example. So we wanted to use this method in order to study disorder-induced phase transitions. So what we wanted to do is study a transition between a conventional topological phase and this anomalous topological phase, and probe how it changes as a function of the applied disorder. The way we add disorder or dirt to our system is by projecting an optical speckle potential into the atomic plane. So initially, usually our experiments work in a way that we try to make the system as clean as possible, and then we can add complexity later. So this is what you see here in green. So we just use a diffuser in order to generate the speckle potential and project it into the atomic plane. And here you see how we play around with the mode matching condition. So on the left, you see the experimental result when we are in the Haldane regime or conventional quantum Hall system. And we tuned the parameters of this initial wave packet such that the overlap with the edge mode is very poor. So here you actually don't see anything along the straight edge that we have projected into our lattice. While on the right, when we are in this anomalous Floquet regime, we optimized for maximal mode matching conditions with this edge mode. And so you can now put your wave packet at the edge of your system and just ask the question, is there any available in the system, yes or no? And this allows you to probe the topological phase transition between these distinct topological phase transitions. And so this is the experimental result for tuning this as a function of the disorder. And we are quite happy with this result because it's the first time that we are actually able in these synthetic quantum systems to probe the interplay between topology and disorder in a two-dimensional system. Like all the conventional techniques that have been out there before in order to probe Hall deflection and so on are not applicable to disordered system. And so this idea of using a mode matching condition with the edge mode and asking the question, is there one, yes or no, allows us to nicely track the location of this phase transition. So again, here AF, that's the anomalous Floquet regime, H is the conventional Haldane topological regime. And there's a difference between the numerics, which is in gray, and the experiment in blue, just because the band structure has mixing with higher bands, which is a bit challenging to take into account in the numerics. The numerics is just a two-band model description. So it's a simplified description to show that the technique works. And now the next thing that we are going to do is to combine this with bulk localization experiment to look for this new phase that has been predicted in these periodically driven systems where the bulk can be fully localized, but there are still topological edge modes in the system to show that indeed we can generate these new topological phases which do not have any analog in conventional static materials. Okay. Questions, maybe? I pause a little bit before I jump to a completely different topic. So I'll just pause a bit. Okay. No questions, I just move on. Okay, so this is essentially the new topic that I want to share with a few new results that we have obtained recently in the context of simulating lattice gauge theories. And we got very excited, I got very excited about this topic because somehow it opens up a new field, like a new direction for us to explore many areas of physics, since gauge theories really appear everywhere and range from topological quantum computation, but also appear in the emergent description of strongly correlated electrons in materials and high energy physics. And sort of the dream of the field is that by performing quantum simulation experiments for these class of models, we may be able to contribute to questions that otherwise can only be addressed in like big particle collider experiments. Now that's a long way to go. So this is not what I will talk about today. This is very, very challenging. We start with very simplified models that capture some of these features. And so I want to first explain a little bit what one actually has to do to even be able to simulate any of these types of physics. So if you look at this structure of a general lattice gauge theory, essentially what it is characterized by, if you put it on a lattice, is that there are vertices and there are matter or particles that can move around between the sides of the lattice. But now the fields have their own dynamics. They live on the links, so that they are described by link operators. And if we look at the properties of this model or the dynamics in the system, there's an interaction between these matter particles that can move around and the fields that live on the link. Now, why is this challenging to do? So first of all, we need to realize both these degrees of freedoms. And ideally, we would like to have fermionic matter fields. And the gauge fields or the link operators are really best represented by bosonic degrees of freedom. So that already is a little bit challenging to do. But then, moreover, we need to be able to realize local symmetries or Gauss law. And let me explain this in very simple terms. If you think about having fields in the system, which previously I told you we just imprint by hand, now they have their own dynamics. So we could have charges that move around in the lattice, and we could have electric and magnetic fields. But now you know that there's something like Gauss law. So the distribution of charges is not independent from the electric field distribution. But that means that if in this schematic, these U operators, these link operators represent electric fields, and psi represents your charged particles, then if a charged particle hops from one side to the other, the electric field in between needs to change in a very specific way. It cannot just randomly do whatever it wants. And this is the essence of what makes these simulations so challenging, that is having this specific coupling between matter and gauge field degrees of freedom. I think this field, while it is very old and there have been a lot of experiments on realizing building blocks and also dynamics in 1D systems, really got a new push recently because of new tools that have become available, mostly in Rydberg atom arrays, but also digital quantum simulation experiments, because there's much more flexibility and programmability in what you can do locally. Like you can apply gates between nearest neighbor qubits, for instance, and this allows you to tailor different types of constraints or local symmetries in your model. So these are two experiments that have come out last year, studying string breaking and particle-antiparticle pair creation processes in these two-dimensional lattice systems or tweezer arrays. And I think what I want to tell you about today is how we engineer or manage to do this now in an atomic simulator that is neutral atoms in these optical lattice potentials. And there's actually some similarity to how this is done in Rydberg atom arrays. And I think I will comment a little bit on this on the next slide. So what we will do is actually start with minimal models of these lattice gauge theories, which has a more direct connection actually to condensed matter physics, but you could reinterpret this in a quantum electrodynamics type of language. And what we have started doing is study quantum dimer models. And for those of you who have never thought about quantum dimer models, I want to explain a little bit what they are and why they are interesting. So historically, their origin really has been in studying high TC superconductors, and there are people in this audience who know much better than I do. But I'll give you a very simplistic or simple view on why I think they are particularly interesting. Now, what is new about them, or also at the time, is that there are local constraints imposed on nearest neighbors. So I schematically drew this on the left-hand side for a dimer model or dimer configuration on a square lattice, where you should think about these dimers as singlets that are localized between nearest neighbors. Now, why is this interesting? You could compare this to simplify or more simpler quantum spin models, where the spins live on the sides of a lattice. And you know they can interact in the low temperature phases. We can find ferromagnets, we can find antiferromagnets. And there can also be interesting phases if there's frustration in the system. For instance, if we put these interacting spins on a lattice. But now these quantum dimer models, which have these hard local constraints on nearest neighbors. So if you want to have a fully packed dimer covering on the lattice, you can play that game. So you follow the rule that a dimer can only be attached to one vertex in the lattice. You can build up different dimer coverings, but there's a hard constraint on these. You can have something like that emergent in the frustrated spin models, but this additional constraint leads to a restriction of the Hilbert space that is then available to your system. And so this can give rise to very interesting phenomena like topological order, as I will talk a little bit about emergent gauge fields and exotic phases of matter. And sort of really this built-in constraint that gives rise to new physics, which you can reformulate in the form of a Gauss law. So in this case, the Gauss law is very simple. I depicted it here. So this cross basically shows one vertex, and there's one dimer attached to it. And if you look at the schematic on the left-hand side with these dimer coverings, you could look at each individual vertex, and you see that there's exactly one dimer attached to it. So there are never two, there's exactly one, and there's never zero. And this is the type of constraint that we want to simulate in our systems as well. And maybe just to make the connection back to Rydberg atom arrays, the way to do it in these systems is to use nearest neighbor blockade interactions. So the Rydberg interactions are so large that there can only ever be one atom excited to the higher lying state. The nearest neighbor atom cannot be excited, and you can map this onto a dimer. And then again, you get this hardcore constraint in your system. And maybe to think a little bit about this dimer subspace. So this would be the local rules that you have to fulfill. So this defines your subspace. That would be the dimer subspace. And now there's one additional ingredient missing. You need some local dynamics. And the easiest thing that you could do is have these flippable plaquettes, for instance. So this would be a constraint combined with local dynamics. And now you can already see that there's some type of built-in topology, where topology means you can, for instance, define winding numbers along certain lines across this lattice, or you could put it on a torus, you could put it on a sphere. But if the dynamics is given by these flippable plaquettes, there's an even odd number of plaquettes that are crossed by a line. So if the green line is your line that you cut through the system, and you define a winding number for that, if you have dynamics in the system, you cannot connect dimer sectors that have even number of crossings to odd number of crossings. So this gives you, I think, a sense of why maybe these models give rise to interesting properties. There's some built-in topology, and the Hilbert space is restricted that the system has access to. And so this is really what we want. We want to have like these local constraints and combined with local dynamics. And these local dynamics is in fact what is typically challenging to get. Like this type of plaquette flipping terms is something that's very challenging to do in quantum simulation experiments, but it's also somewhat the challenging ingredient in real materials. So I think for both real materials and synthetic systems, engineering this is relatively challenging. So that's why it's also an interesting area, I think, to work on. So long story short, let me tell you how we do it in our experiment. So we work with this two-dimensional lattice geometry, and we found a way to map the dynamics of the atoms in this lattice onto a dimer model or monomer dimer model, where monomers are now isolated atoms and dimers are represented by double occupancies. And the way this works is that along one bond, we engineer the Hamiltonian in a way that we have only correlated processes that happen. That is, two isolated atoms separated by two sites can combine resonantly to form a doublon. And then we relabel these atoms as isolated atoms being monomers and doublons being dimers. So a link can only be occupied either by 0 or 2, and a vertex can only be occupied by 0 or 1. And that's the only processes that happen. All the other ones we penalize by energetic means. So we add potential energy offsets to suppress them. So this is the mapping, and that's really all that happens. And then we look at the dynamics, and we can also give an additional energy cost to the dimers by detuning this process from resonance. Okay, so that means if you look at this Hamiltonian, which has this coupling term between monomers and dimers, and you look at the dimers, if you penalize them in energy, either the dimers become the low energy sector or the monomers become the low energy sector. And this is something that we will make use of in a bit. Okay, so if I now go back to formulating this local constraint or the Gauss law, then it's similar to before. It's essentially a dimer that is attached to the vertex. But in addition, a valid configuration is also now having one atom on the vertex of the lattice. So either one of these configurations is allowed by the local constraint or by Gauss law. And this is a U1 symmetry. And if you now look at the schematic on the left, the nice thing is that we can actually easily check experimentally if this Gauss law is fulfilled just by doing a pattern analysis. And so this is how it looks. In the upper left corner, you see how an experimental snapshot would look like. So this is just finding the atoms in the lattice. And then in the color code below, this is how we reconstruct the atomic distribution in the lattice. So we color coded double occupancies in blue and single atoms in green. And typically the region of interest we analyze is about 50 by 50 lattice sites. Okay, so we have explored this model and we made sure that indeed we can fulfill Gauss' law. So let me just jump a little bit ahead to the physics of this model, which you can most easily see in the spectrum. So I already mentioned that the ground state configuration can be controlled by changing the energy penalty of the dimers. So if you look at the spectrum and you go all the way to the left, there's a unique ground state in the system, which would be this all monomer filled state. And this is a unique ground state. If you go all the way to positive mass, then the favored configuration energetically would be a dimer covering. But now, as I explained to you the local rules, there are really many of these configurations that they are nearly degenerate in energy. And the question is, if we start from this all monomer state, the one in green, and we ramp across this resonance condition, what state do we get after performing this non-equilibrium ramp? And there are these ideas out there already for some time where you can hemidiabatically or non-adiabatically ramp across this resonance. So essentially you try to very quickly go into this dimer subspace without creating too many of these monomer excitations. And this should allow you to generate small U1 spin liquid puddles in this 2D square lattice, which is a coherent superposition of these dimer coverings. And this is a very interesting phenomenon because actually this U1 spin liquid on a square lattice is not stable. And there's usually no way to generate this. So being able to generate this in this non-adiabatic way is quite interesting. And we have performed this experiment. I'll just quickly show you some snapshots. So this is actual experimental data. And I tried to highlight a little bit where these spin liquid puddles are. Looks like we typically have a size of about 7 lattice constants or up to 10 maybe in the size of these puddles that we find in our system. And we have quite a lot of tools to look at the properties. So we can look at the amplitude of the dimer coverings. We can check if they are homogeneous, which seems to be about the case within these puddles. And we can also look at the dimer-dimer correlations as a function of position, which seems to follow the expectation from this ideal RK wave function, which would be 1 over R square. It's always challenging to extract this from experiments, so this is not a fit, this is just a line. But all of this seems to match quite nicely with what we would expect. And I did not include that in the slides, but by now we also have results that actually show that we have the coherent superposition between the dimer coverings. So this has been a quite nice non-equilibrium experiment that we were able to study in these dimer models. And with this, I'm at the end. So maybe to just put all of this a little bit more in context again. So I've talked a lot about these analog quantum simulations where we do Hamiltonian engineering, where we have these nice large systems and long evolution times. We are also started a little bit working on the digital quantum computing space, where the question is about how to get to fault tolerance. But what I wanted to highlight is that there's this big area in between that we can explore, where we now have these synthetic quantum materials in their own right, and we can start to develop new probes and sensors in order to extract information from these systems efficiently. And some of the tools we developed, I mentioned, like these nearest neighbor rotations, but we are now also working on time reversal protocols, and we have looked at subsystem return probabilities to make these systems more and more programmable. And with this, I would like to thank the people who have actually done all the work, especially the cesium team, and thank you for your attention. Sorry for being a bit over time.